Hello! Welcome back to another episode of Plastic Podcast, the show that tells the story of plastic, how we got here, where we are, and where we need to go. I'm your host, Clark Marchese, and this week we are serving science. Today, we are going to be talking about microplastics. We will get a formal definition of what a microplastic is later, but many of you probably already have heard of them. They are basically just tiny pieces of plastic, some of them smaller than the eye can see. I first remember hearing about a microplastic in the context of the ocean, and how when we wash our clothes, plastic fibers sort of leach out into the washing machine, and the same way that Nemo finds his way to the ocean when he goes down that dentist drain, the microplastics do too. So yes, they are in the sea, but they're also everywhere, like seriously everywhere. We find them in the air, the soil, in our food, even Antarctica, which we will mention today. But because microplastics are so all over the place, where they are and how they get there can't be covered in just one episode. So they will continue to come up in the future. But today, we are speaking with one scientist in particular who spearheaded a global study of microplastics to discover just how all over the place they really are. Her name is Abby Barrows, and she has a wide range of research interests. In addition to being an expert in microplastics, she is also a marine scientist and an oyster farmer. We got to talking about her journey as a scientist and how she became interested in microplastics. She also taught me a lot about what a microplastic really is and how they are harmful both to the environment and to our health. She also shared about conducting a global database project that tracks concentrations of microplastics all over the world, what we can learn from this study, and also the importance of citizen science. She is a super interesting human being who has made a lot of scientific contributions to the world and only plans on making more. So I was super happy to speak with her, and I hope you enjoy our conversation. All right, so the first question is, and I like to leave it open, is if you can just sort of introduce yourself and tell us whatever you think is important to know.
All right. My name is Abby Barrows. I am a marine research scientist and also an oyster and kelp farmer. So I wear a couple hats. I have my master's in human ecology and philosophy, and got my Bachelor of Science from the University of Tasmania in Australia. I currently live in Maine, where I was born and raised on a small island, and I try to integrate the work that I've learned, or the things I've learned through my work, into my daily life in terms of reducing plastic and spreading awareness around plastic.
So for all of the future scientists out there who might be listening to this, I want to talk about your academic background and if you always knew you wanted to be a scientist, how did that go for you?
I don't think I always knew I wanted to be a scientist, but the ocean has always been a really big part of my life. I grew up on an island, and I currently live on an island, and find myself attracted to islands all over the world. And that sort of morphed into an interest in science as I progressed through elementary and middle school and high school. And I think it became clear to me that I liked working outside. I liked getting dirty. I had an interest in animals. And so that sort of naturally evolved into wanting to pursue the sciences. I found myself in Australia after high school because I participated in the woofing program, Willing Workers on Organic Farms. It's a great way to travel and stay in foreign countries. I fell in love with Australia. I woofed for 6 months over there, and I decided to pursue my undergraduate degree in Australia. I did a year at the University of Wollongong, which is just south of Sydney. And that first year, I enrolled in a marine biology degree, but I spent a lot of time surfing and not really being a good student. And I'm like, what am I doing? I'm here, I'm like surfing, I'm having a great time, but I'm not, I'm spending money on education. I'm not really digging into it. Is this really what I want to do? Science, what I want to do. And so I paused and reassessed, and I decided to apply for a position with a master's student in Australia who was doing research on the canopies of old growth and new growth temperate rainforest species, eucalyptus trees in short, and looking at the biodiversity of insects in those canopies. And so I said, okay, I'm going to go and do this for 6 months and see if science is really what I want to be pursuing. And I fell in love with science all over again. The field research really fed me, challenging. I learned tons of new skills. I got to nerd out and learn a bunch about insects and microscope work and climbing trees and camping out in the field. And I'm like, yes, this is what I want to do. And so I transferred to the University of Tasmania and into their Bachelor of Science program, majoring in zoology with a minor in geography, and finished out my degree there.
That's super cool. I love that story. And I think a lot of us sort of don't exactly know how our paths are going to unfold. But I am curious how insects in the jungle turned into microplastics in the ocean. How did we get there?
Yeah. So yes, in my final year at the University of Tasmania, I did an independent study on seahorses, looking at their diversity, distribution, and trade in Southeast Asia. And I got really into the project, learned a bunch about seahorses, and I applied to be the research assistant on this 2-year, with the second year of this funded project to look at seahorse species in Papua New Guinea. After I graduated, I went to Papua New Guinea and worked on this in this field research station. Through that project, I encountered so much plastic in a way that I had never encountered. So I'm trying to study this amazing little creature. And we were in the mangroves, we were in the open water, we were in the reefs, and everywhere I was going to study and quantify the seahorses, I kept on running into plastic. And, this is a remote area in Papua New Guinea, but, it's subsistence living. People are fishing with hand lines. I dug out canoes. I'm like, where's all this plastic coming from? This is nuts, up to my knees in the mangroves and plastic bottles and things. So that was my first sort of intimate interaction with plastics while I was trying to be a biologist. And I continued to travel throughout Southeast Asia after that contract ended and just kept on running into it, snorkeling and diving in Indonesia and just being like, whoa, coming up and breaking the surface and just being surrounded by plastic. And it just kept on sort of getting in the way of me trying to be a biologist, learn about these animals. And it was almost like it was banging me on the head, like, what's going on here? And so it sort of wove its way into my career in a way that, looking back, it was really clear that I was becoming more and more interested in plastic pollution and plastics and how we use them and how it's affecting the environment and the animals that we still have so much to learn about. And I started to do water quality monitoring through a research organization here in Maine. And that's when I first learned about microplastics. I was running a little summer program for teenagers to learn more about marine issues. And we had the students look through the microscope, and I looked through the microscope, and I was like, wait, what? This is all plastic? I mean, we literally just walked down to the ocean and scooped up some water and filtered it. And this is what we're seeing? There were just so many questions. This was back in like 2012. And there's, a few papers published on it, but there was very little public knowledge about what microplastics were and where they were and what it was doing. So that was sort of the beginning of my journey.
Well, that's interesting how it started out with plastics that you saw all around you, and then it ended with stuff we can't even see. I think most people will know what a microplastic is or have heard the word at least, but just in case, can you just tell us what is a microplastic?
Right. Okay. So microplastics are defined, well, depends on where you are, but microplastics generally are defined as a piece of plastic that is less than 5 millimeters in size and down to 1 micron. And anything below that, smaller than that, is considered a nano.
Okay, so in case any of you are having a hard time visualizing how big is 5 millimeters long, I asked ChatGPT for a short list of things that are 5 millimeters long. Number 1, we have a grain of rice. Number 2, the tip of a freshly sharpened pencil. 3, the legs of a staple. 4, ladybugs.
So, being a ladybug automatically makes me a girl. Is that it?
And 5, a SIM card. And that last one is in fact plastic itself. So now we know anything this size or smaller can be called a microplastic, which is actually a bit bigger than I had expected. I thought all of them would be, close to invisible.
Microplastics can come in a variety of colors and shapes, with the most common shape being found in the environment is a microfiber, which is like a little piece of hair. It's really important to think of microplastics not as one thing, but as a suite of contaminants, because they can be made out of all different types of plastic, all different additives, dyes. And generally, microplastics are divided into 2 categories, which both have really different regulatory aspects. So we have the primary microplastics, which are plastics that are made on the micro level. So think of things such as microbeads, which are used to be in personal care products as a filler or as an exfoliant, or it can be in your toothpaste as an extra abrasive. A lot of those have been taken off the shelf with some legislation that was passed in 2018, because those were directly making their way into our environment through just washing them down our sink drains. Then there's also the nurdles, which are a primary microplastic. And nurdles it's a funny word, but basically it's just a little plastic pellet, which is about the size of a lentil. And those are sort of feedstock for creating so many of our everyday products, from plastic forks to Tupperware to computer cases. And those little pellets are shipped all around the world to factories where they're melted down and different additives are put in to make them into those items. Those pellets often are spilled into the environment, and there's been some pretty spectacular pollution events. Those little plastic pellets have been found to hold and concentrate chemicals in the ambient environment up to 1 million magnitudes higher than what is found in seawater. So those little pellets can be super toxic, and they travel all around the world in our ocean currents. The other type of microplastic, which is what we most commonly find, are the secondary microplastics. So these are plastics that have been created through the fragmentation of larger pieces of plastic. So think of anything from tire wear. So we all have to replace our bike or car tires, every few years. Where is that going, right? It's shedding into the environment. That's a type of microplastics. Styrofoam cups. I don't know if you've ever done any cleanups, but you go to grab a styrofoam coffee cup and it just shatters, and that turns into a microplastic. And probably the largest contributor of microplastics, in particular microfibers, the secondary type, are from our clothing. So each time we wash, dry, or wear our synthetic clothing, it's shedding into the environment, sometimes thousands of particles per garment. And so that's another way that microplastics make their way into our planet.
Okay, you taught me something I didn't know. I thought, and I think a lot of people assume, that microplastics are the secondary kind. I was going to ask in my question, there's no microplastics factory, but I guess that there is.
Unfortunately,
yes. Another question, I think we don't exactly know how harmful they are, or all the ways that they are harmful, rather. What can you say about the research that we know for certain, and then also anything about the fact that we don't know?
So microplastics appear to be basically everywhere. When I first started doing research over a decade ago, I was convinced that there are places on the planet that didn't contain plastic. Unfortunately, that still remains to be seen. I mean, samples from ice cores, from the mid-ocean ridges, some of the deepest parts in our oceans, from our mountaintops to our alpine lakes, to our beer and our honey and our breast milk and our bottled water and our groundwater, we are finding plastic, microplastic. They're in our air, they're in our clouds. It appears that we've done an amazing job of covering the earth in plastic particles in just, 60, 70 years. And the scary thing is that we don't really know what the short and long term. We know that we're ingesting them. We know they're in our lungs. We know we're breathing them in. We know we're in our food. But the scary thing is not knowing how the toxic additives that are in most plastics, so over 50% of plastics are made with known hazardous additives. A lot of those have not been tested. We don't quite have a grasp as to how this is going to affect us in the long term. But for me as a scientist, I think we need to be operating under the precautionary principle. And it's really important to proceed with caution, even though at this point we're really living in a very plastic world.
I am also very on board for this precautionary principle, and I suppose in the meantime we can continue looking into the ways in which they might be harmful. But let's start with what we already do know about their harms. Perhaps maybe we'll start with the environment. I want to circle back to something that you mentioned that I did not quite understand. And when I was doing a bit of reading for the episode, I came across an excerpt explaining the same thing, but I don't think I get it. I wrote it down. It says that microplastics act as a sponge for pollutants already in the environment, absorbing and concentrating chemicals many magnitudes higher than the surrounding water. I read that and I said, what?
I can try to break that down. Yeah. Plastic is made out of oil, which basically acts as a fat in the environment, right? Oil, think fat. And microplastics are very small, but they have a large surface area. And that surface area has the ability to attract and absorb ambient chemicals that are in the environment. So plastics are considered lipophilic, which means fat-loving. So they attract other sort of fatty things. And they're also hydrophobic, which means they don't bond to water molecules. And so think of the ocean. In the ocean, we have all the things that are in the atmosphere and that we've been using and dumping to the ocean for centuries. In the marine environment, there are all these sort of noxious, toxic chemicals floating around. And this little piece of plastic, which is fat-loving and not binding to water molecules, it's sort of just floating around. That plastic is also made with some of these hazardous chemicals, but it also attracts those hazardous chemicals. So as it floats around, it's pulling these things out of the environment as it sort of bumps into them and in proximity to them. So this piece of plastic, which already had some hazardous levels, now has elevated how toxic it is because it's been picking up the stuff that's in the environment. A study that was done by Takada, actually a Japanese colleague of mine, looked at those plastic pellets, and he found that one little plastic pellet can concentrate chemicals up to 1 million magnitudes higher than the surrounding seawater.
Okay, you're teaching me a lot of things today. Would you say it's a useful metaphor to compare it to the way that we know that a rainforest or the ocean is like a carbon sink for the carbon in the atmosphere, but the microplastics are like a toxic sink for the toxicness of the ocean?
Yes, I would say that that's an apt analogy.
Okay, so that sounds bad, but what is the implication of having these ultra toxic pieces of plastic in the sea or these toxic plastic sinks?
So this tiny little piece of plastic is actually extremely toxic. And that little piece of plastic can be ingested by any number of sea creatures. We don't know how many of those toxins, once they're in the animal, are then migrating out of the plastic and finding permanent residency in the fats of that animal. Again, right? It's like that play of fats, like the plastics are made out of oil, so there's a certain amount of affinity there. But if it's in the animal lung, there's some fatty tissue or some of those toxins then migrating to the fatty tissue of that animal. And that interplay is something that we still are trying to understand. We also know that microplastics are small enough that they are moving through the blood membrane barrier inside of animals and then can enter the circulatory system and find a more permanent place in that animal.
Okay, so just to take a moment for listeners who might not be familiar with these concepts, this is touching on both bioaccumulation and biomagnification. And I think that they're important to understand, so I'm going to take just a minute to break them down. Bioaccumulation is what happens when an organism ingests a particle, and usually the particles we're talking about are toxins, and in this case plastic, faster than they can digest them, or they simply cannot digest them, and it builds up or accumulates in their fat cells or bones. And in this process, the toxins are coming directly from the environment. Biomagnification, on the other hand, happens when the toxins or plastics build up along the food chain. So let's say you have a sea urchin and it has plastics in it through bioaccumulation, and then you have a squid, and the squid eats the sea urchin and the plastics inside it. And then you have a tuna, and the tuna eats the squid, but it's also eating the plastics from the squid and the sea urchin, in addition to the plastic it ingests from the plastic that's just floating around in the ocean. And then finally, you have a human who eats the tuna. So your tuna salad has plastic from the tuna and the squid and the sea urchin and the plastic that came from the plastic that the tuna was wrapped in. So all of this to say, bioaccumulation results in higher concentrations of plastics within individual organisms, and biomagnification is the effects of that as animals pass through the higher rungs of the food chain. So why is this a problem? The answer is we don't exactly know definitively. There's why is this a problem for us humans, which I'll start with, and then why is this a problem for the squid? For us humans, the good thing is that there are a lot of scientists out there working on understanding the way that plastics or ingesting plastics has on human health. The problem with health research, though, is that a lot of these effects might not be seen for a really long time. So we can see if a person has a certain amount of plastic inside them what effect is that having on them now versus what effect is that going to have on them over the course of their lifetime, over the course of decades. And that data just hasn't really come out yet. The other problem with health research is that it's really hard to pinpoint causation. So let's say you spend your entire life accumulating plastic inside of you, and then you have a particular health outcome. How do we know for sure that it was because of the plastic? Or, for example, could it be due to some genetic predisposition to that outcome? Or perhaps a lifestyle choice? Or perhaps some other external factor entirely? Or even a combination of them all? So the point of this is that if you have a particular health outcome throughout your life, it's really difficult to say that it was because there was too much plastic in your tuna salad. This might be all the more reason to take the precautionary principle, as Abby Barrows tells us, because just due to the fact that we cannot prove direct causation doesn't mean that plastic isn't having an impact on our health. And without a clear line of causation, it makes it really difficult to regulate against. Now, when it comes to the squid, we're actually going to be having a conversation about overall marine health. Similarly to humans, we don't exactly know how ingesting plastic is going to affect the long-term health of squids. But what we do know is that every organism in the ocean performs a very specific function in its ecosystem. So if it is in fact the case that plastic has a compromising effect on the long-term health of the squid, or maybe I'm getting hung up on the squid. It's not just the squid. If plastic has a compromising effect on the long-term health of any organism in the ocean that prevents it from fulfilling its essential role in the ecosystem, we can start to see overall health of ecosystems decline and greater biodiversity loss. There are a lot of consequences with biodiversity loss, which is probably an entire podcast altogether. I want to sort of switch gears a little bit to talk about a project that you did to create a database of microplastic levels around the ocean. Can you tell us all about this project, how it was conducted, and what we learned from it?
Yeah, absolutely. So in 2013, I partnered with an organization called Adventure Scientists. They're based in Bozeman, Montana, and they strive to solve some of the world's most pressing environmental problems, which access to data is crucial for resolving them. And so they do that through connecting scientists with adventurers, basically citizen scientists on steroids, people who are able to, paddle around the Arctic Circle or row across the Pacific, people that have the means and the drive to go to some of these more remote and difficult to study areas of the planet.
Okay, really quick. If that sounds like you, I have put a link to Adventure Scientists in the episode description.
And so through Adventure Scientists, we launched the Global Microplastics Initiative, which ended up being a 5-year project that we looked primarily at microplastic concentration and distribution in surface waters around the world. We started with the marine environment, and I think 2 years into the project, we expanded into freshwater environments. So sampling on all the continents on the planet and in all the major oceans. They collected over 2,600 microplastic samples. And so when I say a microplastic sample, I mean a 1 liter bottle of surface water. And those samples were filtered onto a 0.45 micron gridded filter. So whatever was in that sample was left on the filter. And then I would put that filter underneath the microscope and using that grid, move through, kind of like mowing along back and forth to count and quantify what types of materials and plastics I was finding on it. I would filter it, look at it, and then I would mark down what color plastics I was finding, what shape they were, and approximately what size.
Wow, that's a lot of work. What did the study find?
And we found that 80% of the marine samples were plastic that we were quantifying, and about 50% of the freshwater samples. So just because they're not plastic doesn't mean they can't do harm to the environment. So even when finding semi-synthetic and synthetic microfibers and microparticles, those still can act similarly to plastic in terms of absorbing some of those toxic chemicals. A lot of even natural and semi-synthetic materials are made with hazardous dyes and things like that, other additives that also can cause harm. The big thing with the non-synthetic particles is that they just break down faster and release those chemicals a little faster.
Okay, quickly to summarize, this study was looking for plastics which are synthetic materials, meaning they are not found naturally in nature. And the results of the study show that synthetic plastic material were found in 80% of marine samples and 50% of freshwater samples. What Abby Barrows was saying at the end is that even the samples that did not contain plastics may still contain other materials put into the ocean by humans that are harmful to water environments. This can be non-synthetic materials such as cotton or wood, which despite being found naturally in nature, firstly, do not belong in the sea, and secondly, can still be treated with dangerous chemicals. Or secondly, semi-synthetic materials such as rubber or nylon, all of which have similar effects as plastic on ocean health. So if you were thinking to yourself, 80% isn't so bad, well, the other 20% is not necessarily uncontaminated either. One thing I really want to know is if these findings were distributed evenly across the entire ocean, or if we see certain areas having higher concentrations.
The takeaways from the marine study was that we found higher concentration of plastics in the polar regions, and we found more plastics offshore than in the nearshore areas, which I thought was interesting, but it makes sense because a lot of those plastics get trapped in these gyres, these big areas of convergent currents out in the ocean. There's 5 of them on the planet. And so some of these plastics maybe, could be 50 years old and they just get trapped in there and go around and around. Same for the polar regions. It seems like they're kind of a dead end zone for the plastics. They kind of get trapped up there. Additionally, that data set is one of the largest global data sets on surface microplastics in the world. For me, it was really important that data was accessible to people. And it's open source data. You have to go through the Adventure Scientist website to access it, but it is available to whomever wants to use it for whatever they might want to use it for. And since then, it's been used by governments around the world to help inform marine protected areas. It's been used for different companies to try to reduce the amount of plastic that they use in their companies. It's been used by the World Health Organization. It's been really great to see that data set and all that energy and effort that went into that 5-year study continues to be useful for people to reduce plastic in their communities.
Wow, that really is incredible. So first of all, thank you. And second of all, congratulations. And for anyone who is interested in accessing that data for whatever you might want to use it for, as I said, the Adventure Scientist website link is in the episode description. I do have a couple of follow-up questions, though. The first is just a curiosity thing. What was the reason for controlling the different colors of plastic? You said you sorted them based off of color. What were you hoping that would reveal? And then secondly, you also mentioned that this was a surface water study. I'm wondering if you think that anything more could be revealed by looking at levels of deep water.
Okay, I'm going to take your second question first. We did do some depth sampling. We utilized scuba divers to take samples at different depths, basically as deep as scuba divers could go. I can't remember if we actually incorporated that data into our global paper, but I found it really interesting because we found a lot of plastics at depth. More and more research has since come out that there is a lot of plastics throughout the water column, which is alarming, but also important to know because that's where animals hang out, right? Some hang out right at the surface, but really things are living in that water column.
Okay, water column. I got to do it. I'm a definitions girly. I don't know if any of you did this science experiment as a kid where you get like a clear tube and you take equal parts of corn syrup, vegetable oil, water, dish soap, and then you pour them all in. They're all different colors and then they separate and you're like, what? And when we did this, we learned that this happens because all of the liquids have a different density. And you do see this happen in the ocean as well. You can imagine this tube going all the way from the surface down to the ocean floor. And we have 5 separate defined layers. And we call these layers the water column. The layers are not so stark as we can see in the science experiment. The water can, mix freely amongst itself. But it is just useful for scientists to define the different layers because density is not the only change in the ocean that you see as you go deeper. The amount of sunlight, for example, changes as well. And this can affect which species can live there. So it's useful to have these cross sections.
And we found much higher concentrations of plastics throughout the depths than compared to the surface.
And that changes their buoyancy.
So yes, there's a lot more questions that could be answered. Better understanding how plastics move in the water column, mixing zones, fouling, and how they sink and then come back up. After they've been, the deeper they go, the less light penetration there is, and so probably less algal growth, and that changes their buoyancy. So there's a ton of different questions and angles. Your first question regarding color. The reason we did color, a few different reasons. One, it was like one very easily identifiable thing, the morphology of the plastics, color, shape, size, bam. We also found that color is an interesting thing for a few different reasons. One, animals might be attracted to certain colors over other colors. So that's like some information that then could be pulled out from this data set. Two, now that we're finding with airborne microplastic, the color potentially could affect microclimates. in terms of concentration of airborne microplastics. If they're dark, they're going to absorb sunlight. If they're transparent, it's going to pass through. So that could change heat trapping or heat movement in different areas. So that's, as a scientist, trying to think about what data can I collect that then could be utilized beyond the study as well. The other thing is, I never did it, but we potentially analyze some of the dyes and toxicity of different dyes as well in plastic. So having that color and be like, we're seeing a lot of blues and blacks. What sort of dyes are used to create that color? And what are the toxicity levels of those dyes?
Okay, I was thinking like, my brain, I'm not a scientist, so I was like, are they trying to see if there's like more, these are Coke bottles and these are Pepsi, or like
my favorite kind of Pepsi's Pepsi.
Something like that. But
I wish the smoking gun was so clear. Unfortunately, it's really hard to pinpoint, or basically impossible to be like, this little fragment of plastic is from, really hard to say like, this came from a Coke bottle. Same with all the microfibers. We were hoping we could like trace it back to some type of textile. It's unfortunately not as a direct correlation as you would hope.
I'm wondering, were you surprised by the fact that there was a concentration in the poles? And then I know that you eventually went on to do an Antarctic study. Did this project lead directly to that one? And then also, could you just tell us a bit about that Antarctic expedition?
I think as I learned more and more, and as more literature came out throughout this project, it became clear that the poles were going to be sort of a dead end for plastics. So it wasn't too surprising when the data kept on reflecting that. So after the project wrapped up, I stayed in touch with some of the adventurers that had been key players in the project, either getting samples from really remote areas or getting high volumes of samples in areas that I wanted more samples from. So one fellow in particular, Mike Lebecki, who is a National Geographic explorer and a professional adventurer, you know that is the title. We kept in touch, and we ended up going to Alaska, and I ended up doing a multi-matrix study looking at grizzly bear scat, glacial ice, surface water. So I did a week-long study with him up there, and we hit it off. I'm like, I would travel anywhere where the sky is great. Through that project, another opportunity came up to go with National Geographic and Lindblad to sail to the Antarctic Peninsula. And I love an adventure. I like a challenge. And so getting samples from Antarctica was really great. But what would be even greater was to be able to go and get samples myself from Antarctica. I designed a project that looked at how tourism may be impacting microplastic concentrations in the Antarctic, which definitely there's a little pushback because no one wants to be shown in a bad light as to their business causing pollution. But to me, I'm like, we know this is a problem. Let's get in front of this. We have the means here to get some great baseline data and then potentially use that to incite some change. With Mike Lebecki and then the two filmmakers that I had been on the previous expedition with, Keith Ledzinski and Tommy Jones, Triage Creative, and we did a bunch of awesome science and made a film.
Yes, so a film was made about this Antarctic expedition, and it can be found on Abby Barrows' personal website, abbybarrows.com. And Abby is also working with a couple of colleagues to write a paper to be published about this expedition and the data they found. It hasn't quite been released yet, but we might have to circle back for another episode once it is.
I'm hoping it will really help inform some of the future research in Antarctica, but also be a first step towards potentially making some changes in how we do tourism in some of these fragile, remote areas. And in look at this research, I still have so many questions and so many things I want to study, especially in that part of the world or in the polar regions. And so we're hoping to pull together a all-woman science research team to go down there and do some follow-up research.
Okay, well, it seems like you have some really interesting things coming up, and I'm definitely going to be paying attention to all of them, but we are going to start to come into the final questions of this interview. But before we do, one thing that really is intriguing me about all of these studies is how normal people, or adventurous people rather, played such a big part in doing the science. Can you talk a little bit about the concept of citizen science and how important it is?
Basically, we're citizens, the average layperson, the average citizen, contributes to a larger science project. And that might be through doing some sort of field data collection. And that can come in so many different forms. Also, citizen science is often used for monitoring long-term health of an area. And it's a great and powerful and cost-effective way to gather some really robust scientific data that can really help inform future decisions and also have us better understand the health of our local communities. I also really think citizen science is great because it gets citizens involved in environmental issues that affect them in their local neighborhood.
Okay, listeners, if this sounds like something you would like to take a part in, it might be worth a quick Google search of citizen science in your area. There's literally citizen science opportunities all over the world, so maybe you can get involved too. Okay, the next question is, if there is one piece of policy or piece of legislation which you think to yourself, oh my goodness, we needed it yesterday, this is so overdue, what would it be?
Banning single-use plastic. Single-use plastic that we use for literally seconds and then throw in our trash can. We can't keep on using this material like this. Our landfills are full. We've been shipping it across the ocean. Countries are closing their gates to all of our waste. Everyone's really into convenience, but we really need to scrutinize the true cost.
We are coming to our final 3 questions. The first of which is, what is your favorite part of your job?
So many favorite parts.
You can say it.
I really love designing projects. I really love thinking about bigger questions outside of myself that impact the wider world, but then also have that trickle-down effect to impact individuals. I love gathering data that is then accessible to people outside the scientific world. That's the joy of working with citizen scientists, is that people take on ownership of the project, and just seeing people run with that has been so rewarding in a way that I feel like a lot of scientists don't have that bigger connection.
That's really great. The next question is, I know that a lot of times, a lot of environmental reporting can be sort of bleak, and sometimes that can become heavy. So I want to ask if there's one piece of recent good news that comes to mind about something in your field.
Yeah. There is a lot of bleak news, but there are a lot of amazing people working really hard to change that. And I think I'm often heartened by legislative changes that I didn't even know were in the mix being passed. So, for example, Aldi, which is a big grocer, just removed plastic bags from 2,300 of its stores. And so it's little things like that make me feel pretty good. Even though I know it's a drop in the bucket, we need a lot of drops in the bucket. And I think the other piece is that there's just so much more awareness than there was even a decade ago about plastics use, about microplastics, about toxicity. And people are starting to demand more from producers and more from the companies that they support. So I think that leaves me with hope for what's to come.
Yeah, I think it's really important not to get discouraged, and it's not always easy. And I think it's also important to have sort of patience with ourselves when we do. It can get heavy, but I think what you said also, that just the fact that there are a lot of good people really dedicated to this is good news in itself. So the last question is there anything that we did not talk about today that you think is absolutely important to discuss in a conversation about what we've just had a conversation about?
Going on from what you just said is that, yeah, there is so much that you can really lean into the doom and gloom and the bad news, and they're like, oh my gosh, that things are going awry. And, there's so much pollution and toxicity, and what have we done to this planet? Yeah, you can dwell there forever. But my hope is that through research and through data collection and understanding of the problem, that this will incite people to enact change, whether it be in their own lives or something outside of themselves, rather than make them feel crushed by the overwhelming doom and gloom. I think that trying to twist some of the knowledge about plastic pollution into empowerment to create lasting change is the way forward.
Okay, well, I want to thank you so much for your time. I learned a lot in the last 50 minutes, so I really appreciate you coming on the show.
Thank you, Clark. Thanks for reaching out, and I'm glad we were able to make this happen.
All right, give it up for Abby Barrows, everybody. I'm super glad I got the chance to talk with her. I learned a lot of things today. One thing I did not learn, however, was how we can scoop up all the microplastics in the sea in one fell swoop. But that's because it's not possible. Microplastics are a reality that we have to confront. But as Abby mentioned, her database has already informed major global policy. So I truly believe that learning as much as we can about microplastics is the best way forward, and I hope that you learned something today too. You've been listening to Plastic Podcast. This week's guest was Abby Barrows. You can find more information about her and links to her work in the episode description, as well as some information about adventure scientists. Cover art for the show was done by Laurel Wong, and the music that you're listening to was done by Tadeo Cabejos. I am your host, Clark Marchese, and this episode was produced, written, and engineered by me. So if you hated it, I am the one and only person to blame. If you loved it, I will not only see you here next week, where we will be talking all about zero-waste cities, but if you loved it, I would also really appreciate a 5-star rating and a review. The Plastic Podcast is part of a larger network of sciencey podcasts called Pine Forest Media. You can find more information about them in the episode description as well, or on the website pineforestpods.com and Instagram @pineforestmedia. We've got some really exciting science podcasts coming out this year, and that review I was talking about really helps the entire network to grow. So thank you to all of you who have made it this far, and we'll talk soon.